So when we start looking more at weather maps, one of the things that you're going to see is atmospheric pressure. What's the pressure doing? And a really common weather map to look at is what are the conditions, including pressure at the Earth's surface. And those pressures that we see on the weather map have automatically been adjusted for if they're at upper elevations. That has been taken into consideration, and a certain amount of, I'll put the words up here, a certain amount of pressure has been added back. So I have a couple of examples to kind of show you. So, for instance, if you have a barometer and your elevation is at sea level, then there's no correction required. Okay? So, say your barometer reads 1,008 millibars, you're at sea level, so you don't add any pressure back, okay, because you're not artificially low pressure because you're at upper elevations. So I went ahead and actually, if you printed off the slides, you might not have this slide. You have the slide on the next page. But this actually is a figure from the previous edition of this textbook, and it has 3 examples. And so here we have a location where we have a barometer that's reading the pressure at an upper elevation, 1,000 meters above sea level, and not so surprising, that barometer is telling us that the atmospheric pressure is 915 millibars. But in order to kind of compare Station A and Station B, what you'll see on a weather map is we have added 99 millibars back to that reading. And so you're going to see a barometric pressure of 1,014 millibars for Station B. And Station C is even higher in elevation. It is up another 800 meters. So not so surprising, your barometer is going to read 840 millibars. But it's kind of artificially low because it's up at upper elevation. So notice that what's done then to that 840 millibars is to add 180 millibars. So what you're going to see reported is 120 millibars on those maps, because differences in pressure is very important to kind of get a sense for, quite frankly, the flow of wind. And so what might look like perhaps a relatively low pressure, 840 millibars, honestly, it's only low because it's upper elevations. And so what you're going to see is actually, of the 3, Station C has reported the highest pressure. So here is the same text. Now there's only 2 examples here for this. So again, we have the example of at sea level, you don't add anything back to correct or to standardize for elevation. And here we have Denver, Colorado, and up 1,600 meters, that required to add 172 millibars. Sometimes students will ask me now, am I going to have to be able to do this correction on the test? And the answer is no. But you need to kind of keep in mind, or I might test you over why, I don't know. I might ask you a question, but I might not have you actually do the math. So kind of along those lines, I'm going to bring in these 3, these 3 chambers. And honestly, it's the same system, but the volume of the system was decreased. That's like a movable piston. Okay, and you can kind of see that you add weight, and the piston goes down. You add more weight, and the piston goes down even more. So what's happening here is we have the least dense gas in that chamber, and we have the most dense gas here. And so if we call this A, B, and C, kind of what we've done, and if you're kind of listening to these in order, I kind of drew, if that's the Earth's surface, one of the things we already know is the air is most dense at the Earth's surface. Okay, you go up in elevation, the air gets thinner. Okay, more sparse. You go up in elevation, it gets even thinner. Okay, so this would be the vertical difference in pressure, and so they correspond to correspond to A, B, and C. So, one more slide I kind of want to show you. There's a table. And basically, well, one of the things I've been thinking about recently is we talked about how you can send up weather balloons and get the environmental lapse rate, the temperature, as you go up in elevation. And that's what this last column is. And so just kind of for a typical day, you can see that it's getting cooler. Okay. And then the other thing, these other two columns, this is how high you're going up in elevation. The units are kilometers. And then this is the decreasing pressure, barometric pressure in millibars. So there's one segment. Notice that here we kind of tip in on the Celsius scale from this is all freezing now, getting cooler. Okay. And notice we continue to, as we go up in elevation, of course, the pressure, atmospheric pressure decreases. And then I broke this segment out because, so can you see where we must be somewhere in here hitting the top of the troposphere, like the tropopause, because actually can you see where now as we go up in elevation, it gets warmer. And that should be no surprise because we talked about layers of the Earth's atmosphere. We have the thinnest layer next to the Earth's surface, the troposphere. It's the densest, and then we have the stratosphere. As you go from the stratosphere, temperatures get warmer, so that's kind of what we have here. But in general, check this out. I mean, if this is the tropopause, the top of the troposphere, kind of segueing into the stratosphere. I mean, that is some thin air up there, is my point.